Have you ever just stared at your phone screen and been amazed? The incredible colors, those super deep blacks. It honestly feels a bit like magic. But behind every single one of those perfect pixels, there's a world of really, really complex science. So let's get into it and unpack what it actually takes to build the perfect screen. We're always hearing about the future that this tech is going to unlock, right? We're talking foldable phones, screens that are so efficient they barely sip power, and even wild applications in things like augmented reality and medicine. The potential is, well, it's just staggering. But here's the thing. Take a look at this timeline. The journey from a pretty simple OLED display way back in 2003 to the kind of state-of-the-art screens we expect now, that's taken over 2 decades. In the tech world, that is a long time.
Which kind of brings us to the big question for this whole explainer. If this technology is so amazing, why is it so incredibly hard and, time-consuming to get it just right? What's the holdup?
Okay, so to answer that, we've got to first understand the fundamental problems that scientists and engineers are wrestling with day in and day out. These are the big roadblocks standing in the way of perfection. It really all boils down to these key challenges. It's this constant battle, right? You're trying to crank up the brightness, make the screen last for years and years, and keep those colors perfectly pure. And on top of all that, the different colored pixels wear out at different speeds, which leads to that dreaded screen burning. Getting all of these right at the same time, well, that's the grand challenge.
But the tech issues, they're really only half the story. The real reason progress has been kind of slow points to a much deeper, more fundamental problem with how the research itself gets done. And this quote just nails it. See, you have these 3 critical groups of scientists. You've got the theorists dreaming up the ideas, the computational folks modeling those ideas, and then the experimentalists who actually build and test them. And historically, these groups have been working in completely separate worlds. So let's just compare these 2 ways of working. The old, fragmented way means everyone is kind of stuck in their own lane. Progress is slow, you waste a ton of time and money on ideas that go nowhere, and your predictions are, let's just say, not always reliable. But the new, integrated way, it's all about constant collaboration. That leads to rapid, laser-focused discovery, way more efficiency, and insights you can actually use. So, the solution is pretty clear. You've got to build bridges. You need to create a framework that gets these different fields talking to each other, working together, and creating this powerful loop of discovery and proof. And the benefits of doing this are just massive. When you get everybody on the same page, the direction of the research becomes crystal clear. You stop spinning your wheels and wasting money on dead ends, and instead focus on the problems that will actually move the needle. It just makes the science better, faster, and more reliable. This whole integrated approach is often called a design, make, test, learn cycle. It's this beautiful loop. You design a new molecule based on theory and computer models. You physically make it in the lab. You test its properties to see what it can do. And then, this is the most important part, you take everything you just learned and feed it right back into the next design. It's a continuous, super fast cycle of innovation.
Okay, that all sounds great in theory, but what does this actually look like in the real world? Let's dive into a really fascinating case study that shows exactly how this framework helped solve one of the biggest problems in OLED efficiency.
So here's the core issue. Because of some pretty fundamental physics, for every 4 units of energy you pump into a basic OLED, only 1 of them actually creates light. The other 3, these things called triplet excitons, are totally wasted. They just turn into heat. That is a 75% energy loss right out of the gate, which is just wild. So, the holy grail has been finding a way to capture all that wasted energy. And scientists discovered this really clever mechanism to do it, called thermally activated delayed fluorescence, or TAD for short. Basically, TAD is a trick that allows a molecule to grab those useless triplets and convert them back into useful light. In theory, it could get you to nearly 100% efficiency.
And this is where that integrated approach becomes the hero of the story. The experimental team proved that TADF was actually happening. Then, the computation team jumped in and figured out the physics of how it was happening. It had to do with specific molecular vibrations. But then, the device team built an actual OLED and found that even though TADF was real, the efficiency in the real world was still really, really low.
Now, if these teams had been working separately, they each would have had an incomplete puzzle piece. But by putting their results together, they pinpointed the exact problem. The process of converting those triplets back to singlets, it's called reverse intersystem crossing, was just way too weak and slow. Think of it like a faulty valve that was only letting a tiny trickle of that wasted energy back through. That was the bottleneck. And you could only discover that by bringing all three fields together.
What's so cool is that this powerful way of doing science isn't just about making our phone screens better. No, the implications are much, much bigger than that.
This exact same integrated methodology, this design, make, test, learn framework, is basically a blueprint for speeding up progress on some of humanity's biggest challenges. I mean, we're talking about everything from creating clean hydrogen fuel with sunlight, to building better batteries, to advancing quantum computers, and even building smarter AI.
And that's really the ultimate takeaway here. By bringing theory, computation, and experiment together, we are creating a faster, cheaper, and way more reliable path to turn a cool scientific discovery into a real piece of technology that can actually change the world. It basically de-risks the whole process of innovation from start to finish. It's a fundamental shift in how we tackle deep tech. From better pixels on our screens to a better planet, it all starts by bridging these gaps in science. And it really makes you wonder, doesn't it? What other massive challenges are out there that are just one integrated framework away from being solved?